So I got a backlog, but I want to look at jump game. It's a really, really common dynamic programming question. So pause and read it right now. But the crux of it is at each index you can jump that number forward. So from 2 you could jump to 3 or 1, and then from 1 you could only jump to the next 1. You're trying to make it to the final index. And I think almost every approach you can take that's like formal dynamic programming, where you're making an array of the same length as nums, or even something where you're changing the values of the elements in nums, you can pretty much always consolidate it down to a greedy solution where you're keeping track of one number instead of an array. And I'll just show that. So if we try and use an array, if we say something like dp equals, let's say 0 times n, and then we'll define n. We the length of the nums. And then let's say, okay, we want to keep track of something. The first way to do this problem that to me is the most, you have to think about it a little bit, but it's the most intuitive once you've thought about it, is like start at the end and say, what can reach this? And then if something can reach that, like this 1 can reach the 4, what can reach this 1? So then step backwards. So we can say like 4, well, that's already the end. So dp here is going to always be dp at -1. The final element is always going to be 1. That's always going to be true in that you're always reaching the final element because it is the final element. And then we're going to iterate through, so we're going to have some sort of for loop that's going to look like for I in range n minus 1, minus 1, minus 1, except we really want n minus 2 because we want to start at the second to last. And then we're going to have something, and in the end what we want to return is, let's say, dp at 0. And what that's going to mean is, can you reach the end from the 0th element? So, and then here we probably want to say, okay, does 1, we don't want to ask, does it go past the end of nums? We could put something like, if like dp at I equals nums at I plus I. So, or I'm sorry, nums at I plus I is greater than or equal to n minus 1. So it can, nums at I plus I means that's the total distance you can jump from a given index forward to a certain point. And this is saying you can reach the end jumping from that point. But this would not work because it would just be like, well, this you can reach the end because you're at the end. This you can reach the end. In fact, we don't even really need this. We can just say that. But then this 1, it's not that can reach the 4, it's that it can reach something that can reach the 4. So then we could say something like, if dp at I is, if nums at I is like that, then dp at I equals 1. And then we can have an or statement here and say, or the other situation is if it can reach something that can reach the end. So we would say something like, or nums at I plus I. So if the thing it can leap to can reach the end. But then we reach a problem, for example, it's kind of hard to show, but we reach a problem where we don't always want to just jump to the very final thing in every jump. Like, for example, this 2, we could jump to this 1 and then jump to a 1 and then jump to a 4. And if we run this, it should return true for both of these. But let's say we had a situation like this, where the only way to reach this 4 is with this 3. And the 3 will even, if we say print dp at the end, the 3 will even show up as 1, aka true. That I'm using 1 to mean true and 0 to mean false. And what this means is 3 was tested, it counted back and said, you can't reach the 4 from this 0 because you're stepping forward no amount. You can't reach it from this 0. You can reach it from this 3, but then it looks at the 2 and it says, Well, jump forward 2, go to the 0. Does that work? No. So then 2 doesn't work. So the problem that you encounter here is that you have to check every single thing in that jump. And the moment you do that, that's on the order of O of n. So you're talking about then O of n squared for the entire thing, which is too much time. And we want to get it down to O of n. So then you can think, well, if you can ever jump past something that can reach the answer, then you can also jump to something that can reach the answer. So really what we want to do is we want to have some sort of variable like ans, and then let's say ans is n minus 1. And every time we set dp at I to 1, we're also saying ans equals I. AKA what we're doing is keeping track of the earliest thing that can jump to the end. And then here, instead of checking can it reach the end or can it jump to exactly something that can reach to the end, we just say if nums at I plus I is greater than ans or equal to ans. And now this will work, and this will just, unless there's a typo or something, run for every case. But then we look at it and we just don't even we just don't even use dp. Like right here, we could just say ans equals 0. Return ans equals 0. Does the 0th element make it? And in this situation, dp is kind of cool because we're seeing which elements, if we reset our test case, we're seeing which elements can reach the end, but we don't actually need it. We can literally just delete it. And then we have a situation where we're not using an array at all. We're just keeping track of the earliest thing that can reach the end, counting backwards from the end. So this is the first kind of greedy solution, and I think this is an oddity. Actually, it should go exactly in this spike. But this one seems, I think, slightly faster. The other solution is counting forwards. And it's a little easier to get trapped in sort of a fallacious way of thinking about this, where you're like, well, we want to try, if we try 2, then we need to try 3 and 1. And if we try 3, then we need to try 1 and 1 and 4, and so on. But we can do something very similar to what we did here. So we say something like for I or we'll say for I x, or we'll say length in enumerate nums, and then I'll just print this for now to show what this will do, and then return false, so one of these will show up true, one will be false. So what we're doing is we're creating this enumerate is a function on nums where we're saying give me every element, and paired with that element give me the index. So 0, 1, 2, 3, 4, and then 2, 3, 1, 1, 4. You can see that's the 0th, 1, 2, 3, 4th element. So then what we can do is we can keep track of something. We can say, we'll say dist equals 0. Or we'll say dist equals nums of 0. And then here, what we can say is every single time we encounter anything, see if we can jump further than our current maximum jump. So say dist equals maximum of dist and I plus length. And then the other situation that we need to look for is if dist is less than I, that means we never encountered anything that allowed us to jump to the current index. AKA we jumped through too many zeros and nothing could make it past that 0. So here what's going to happen is it's going to say, and then return 0. And then let's correct this to return 1. So what happens here is it says, cool, the maximum we can jump to is this 1. And then we encounter the 3 and we say, actually, it's not this 1 anymore, it's the 4. And then we iterate through the entire thing and return 1. Here we say the maximum thing we can jump to is this 0. And then still this 0, and then we encounter this 1, we say still this 0, and then when we encounter this 0, it can just jump to itself. So then when we encounter this 4, I is greater than dist at that point. Dist is still at the 0, but we're past that. So we know that nothing prior to this can jump to this. So if we run this, this is about this almost exactly the same. I think this just has to do with what time it is here. Yeah. The other thing that fascinated me about this is I was like, okay, that makes sense to me that this spike is going to encapsulate the greedy solutions. These are probably some sort of array solution or something. Or slightly suboptimal things. Yeah, lists and stuff. But what are at the very top? And I think actually, interestingly, this problem pulls the curtain back in a way that you rarely see because it's such a commonly done problem. So this aggregate actually is including many submissions. And also, the optimal solution is pretty much always the same. So it begs the question, what possibly is better than that? And interestingly, I looked at this. It's the same formula. This person's saying, this is the same as for I and length in enumerate nums. And then we have this max length that's the current maximum jump we can get to. So it's the formula is the same, but interestingly, this person seems to have bypassed creating a solution, creating a class for solution or anything, or even defining a function. It's just this script that they're running, and they seem to have figured out exactly how to parse the string. And so they have nums, which is a string initially, and then they say, okay, it's not a string anymore, turn it into a list that we can use. So what they're saying is R strip, which means remove, I think that means like remove any trailing characters. So I guess the first thing they do is remove spaces. I'm guessing this has to do with like the input, like returns and stuff like that. And then they say from the first element to the last element exclusive here. So they're cutting off the very first and last elements, which if you think about what the input variables are, that's the brackets in this string that we're giving the program. So take the brackets out and then also turn it into a list split up by the commas. So I'm guessing like on the back end, this is exactly what the evaluator is doing, like that LeetCode has designed. It's just exactly this, but this person's doing it in their code. And then run the whole program, and it looks like this is how the evaluator like receives information back, is by printing into a file, and then in the end exit. So I thought that was really interesting, and I think it's related to this problem because it's the only situation I can see. If you're talking about a problem like a Sudoku solving algorithm or something, that's going to be all over the place. There's going to be a ton of different time complexities, and the best one is going to truly be reflective of the fastest algorithm with every single corner cut. But here, they're pretty much all exactly the same. They're all pretty much this at the top. So it's interesting to see what happens to get that tiny little edge that gets you into this insane percentile. So that's Jump Game. It's a classic problem. People bring it up a lot with dynamic programming, but I think it's actually, which is fair, I think it's a good place to start. I think, though, it's more emblematic of greedy algorithms than anything.